So a very good afternoon to everyone. So I'm Rohit Gehlot and I will be taking the week 8's doubt session for the material characterization course. So in the last week we discussed about the basics of XRD, like the how the X-rays are generated, and then the different filters, about different filters, and how uh, different sources, and also we end up at the scattering of the X-rays. So before starting, firstly, the major application of the XRD can be classified in the five things. First one is the crystal structure determination. Second is the lattice parameter determination. Third one is the calculation of the phase fraction. Fourth one is the residual stresses. Fifth one is the crystallographic texture or preferred orientation. So these five applications are majorly used for the XRD, and then here also the XRD of some specimens are presented. There are the different XRDs. So before starting the lecture, firstly, let's understand what is the diffraction. So a diffracted beam may be defined as a beam composed of a large number of scattered rays mutually reinforcing each other. As seen in the figure, like there is a particle and there is a crystal. These are the X-rays. So they interacted with the single particle and here with the crystal, and then after the interaction there are a large number of scattered rays which are reinforcing each other generated. Then this is called the diffraction. And then if we understand the origin of the intensity versus 2 theta plot, which is the as shown in this first slide of the today's I versus 2 theta. So this is your specimen sample, when this is the incident beam, and then some rays are like completely transmitted. However, some are the diffracted beams, diffracted beam 1 and 2, and then the plot of the intensity versus 2 theta is plotted to obtain the necessary I versus 2 theta plot. If we come to understand the interaction between the uh, interaction of XRD with different like if the XRD is interacting with your crystal, then this systematic peaks are observed. However, if it interacts with an amorphous solid or liquid, then there is a single uh, peak is observed. However, in case of monoatomic gas, there is no single peak is observed. Okay, and then if we talk about the diffraction under non-ideal condition and ideal condition. So firstly, for the ideal condition of XRD, it states that your crystal should be perfect. Then the incident beam should be composed of a perfectly parallel rays, and then they are strictly monochromatic radiation. However, these conditions never actually exist because the incident beam in the most powder diffractometer is divergent, and the characteristics lines from the X-ray tubes have finite spectral width. Okay, so the ideal condition in most cases don't exist. And then if you talk about the destructive interference is produced in all directions except those of the diffracted beams must be understood, because it is a fundamental to the theory of diffraction, and therefore how destructive interference is produced is important. Okay, as it will lead to the method for estimating the size of very small crystals. And if we talk about the condition for the reinforcement, which means that the waves involved must differ in some path length, there should be a difference in the path length which is in phases by exactly an integral number of the wavelengths for conducting the constructive and destructive interference. As seen in this figure, like there are rays 2 and 3. These two rays do not annual each other at wavefront BB dash. This is your wavefront BB dash, and simply unite to form a beam of smaller amplitude. Okay, as seen that the resultant beam's amplitude is slightly reduced than the previous one. So because of the particularly the difference in their path lengths. Now suppose that the angle theta in following figure is such that the path difference for the ray scattered by first and the second planes A and B is only a quarter wavelength. Then what will be the resultant amplitude? As seen here, there are like these two planes, then these are the rays scattered. This is the plane wavefront coming, and then this is the after diffracting is going on. So what will be the resultant amplitude of these incident waves after diffracting? So they will form a beam of the smaller amplitude. So if anyone can tell me the reason why it will be happening? So because as seen in the figure, like here, the reason is the same as the before, as the amplitude, uh, because the two rays are completely in phase. However, the as seen here, but the resultant amplitude will decrease. Then the question comes, how the destructive interference take place, and then for this, how the destructive interference takes place. So the answer lies in the contribution from the planes deeper in the crystal. So under the assumed condition, the quarter wavelength, the rays scattered by the second and the third planes would also be a quarter wavelength out of the phase. Okay, so that is, the rays scattered by the first and the third planes are exactly half a wavelength out of phase and would completely cancel each other. So we can say that when the path difference is exactly one half of your wavelength, then they cancel out each other. Okay, because of slightly so we in the theory, we in the lectures we discussed that the destructive interference is just as much a consequence of the periodicity of the atom's arrangement as it is for the constructive interference. It follows that there is a connection between the amount of out of phaseness that can be tolerated and the size of the crystal. Okay, and then the crystal is very small, and then the result is that the very small crystals cause broadening of the diffracted beam, that is the diffraction at angles near or but equal to the exact Bragg's angle. Okay, uh, so now let's take an example. So if the path difference between the rays scattered by the first two planes differ only slightly from an integral number of wavelengths, then what will happen? Then the plane scattering a ray exactly out of the phase with the rays from the first plane will lie deep within the crystal. Okay, and then if the crystal is so small that this plane does not exist, then the complete cancellation of all the scattered rays will not result. So it follows that there is a connection between the amount of out of phaseness and that can be tolerated and the size of the crystal. So let's take another example. So as seen here, at a diffracted angle 2 theta, as seen here, diffracted 2 theta b, a dash, d dash and m dash, these are the a dash, d dash and m dash, are completely in phase. So these are completely in phase, and then they unite to form a diffracted beam of maximum amplitude. Okay, so the ray b, this is the ray b, makes a slightly larger angle than your completely Bragg angle theta b. That is, it is making an angle of theta 1, which is greater than theta b, slightly greater than theta b, from the mth plane. On the mth plane, below the surface, it is m plus 1 wavelength out of the phase with b dash. Okay, the ray from the surface plane. This means that the midway in the crystal there is a plane scattering a ray which is one half, actually an integer plus one half wavelength out of the phase with ray b dash from the surface plane. So these rays cancel one another, and so do the other rays from the similar pairs of the planes throughout the crystal. The net effect being that the rays scattered by the top half of the crystal and annul those scattered by the bottom half. So the intensity of the beam diffracted at an angle 2 theta is therefore 0. Okay, now let's take another example. So the intensity is also 0 at an angle 2 theta 2, where theta 2 is such that your ray and dash from the mth plane below the surface is m minus 1 wavelengths out of the phase, with ray c dash from the surface plane. So it follows that the diffracted intensity at angle near 2 theta b but not greater than 2 theta 1 or less than 2 theta 2 is not 0 but has a value intermediate between 0 and maximum intensity of the beam diffracted at an angle of 2 theta b. Okay, so as seen here, so this is your thickness of the material. T is m times your d, interplanar distance, and this is the incident B to complete Bragg angle, and these are the other incident beam B, C is slightly more or less than your Bragg's angle, and then these are the scattered beams. Okay, so your intensity will also be 0 at an angle of 2 theta 2. This 2 theta 2 is slightly lesser than your Bragg's angle, and then if similarly from for the m minus n minus n times wavelength out of your phase with ray c dash. This is your ray c dash from the surface plane. So here also the resultant intensity will be 0. So slightly at higher uh, theta 1 and at lower theta 2, the resultant intensity at some particular distance, it will be 0. Now if you talk about the measure of your peak width, that is full width half maximum. So this is your full width half maximum. Okay. So these two shows that your so here we talk about the integrated intensity, which is the area of your uh, this one. So here this is your half times, this is the average of half I maximum, and top one is the I max, and then this lies between your the angle is 2 theta 1, 2 theta 1 and 2 theta 2, and then this is the Bragg's angle at 2 theta b. Okay, so effect of your fine crystallite size on your diffraction curves. Okay, so if you talk about the if you take the difference between these two, then it will be half times of 2 theta 1 minus 2 theta 2, and it will be theta 1 minus theta 2. Then the path difference equation for these two angles are 2t sine theta 1 will be m plus 1 lambda, 2t sine theta 2 will be m minus 1 lambda, and then by subtracting we find that t sine theta 1 minus sine theta 2 will be equal to lambda. And then if we put the formula then for sine c minus sine d, then we can write it as 2t cos theta 1 plus theta 2 by 2, and sine theta 1 minus theta 2 by 2, it will be equal to lambda. And then solving this we will get the theta 1 plus theta 2 will be 2 theta b. So and then for lower angles it can be taken as theta 1 minus theta 2 by 2. Okay, so it can be taken as theta 1 minus theta 2 by 2. So we equate it as 2t theta 1 minus theta 2 by 2 cos theta b is equal to lambda, and then from here we get the relation between your or we call it as a Serrer formula. So a more exact treatment of the problem gives this. So t can be written as 0.9 lambda by b cos theta b. Okay, so let's take an example. So what is the order of magnitude of this effect? So suppose your lambda is 1.5 angstrom and d is 1 angstrom, and then the theta is uh, your theta is 49 degree. Then for a crystal 1 mm in diameter, the breadth b due to the small crystal effect alone would be about 2 in times 10 to the power minus 7 radians, or too small to be observable. So such a crystal would contain some 10 to the power 7 parallel lattice planes of spacing assumed above. However, if the crystals were only 500 angstrom thick, it would contain only 500 planes, and then the diffraction curve would be relatively broad, namely about 4 into 10 to the power minus 3 radians, okay, around point, which is around 0.2 degree. So for non-parallel and non-monochromatic incident rays, if you talk about, so these are the perfectly parallel beams and has never been produced in the laboratory, as any actual beam of X-ray contains divergent and convergent rays as well as parallel rays, and also the any real beam is never strictly monochromatic. So then your copper K alpha line itself has a width of around 0.001 angstrom. This narrow range of wavelength in the nominally monochromatic beam is further cause of the line broadening, which is the measure of which is measurable diffraction at angle close but not equal to 2 theta. Okay, since for each value of lambda there is a corresponding value of theta, for example this. Okay, and now we also discussed in the class about the different factors which affect the relative intensity of the Bragg reflection. So these are the structure factor, polarization factor, multiplicity factor, Lorentz factor, absorption factor, and then the temperature factor. Okay. Uh, so polarization. So if we talk about the scatter, one second. So if we talk about the structure factor, it is given by F HKL is the summation of your scattering factor of a particular type of atom Fn and e to the power 2 pi I iota hu plus kV plus Lw, and for simple cubic, all reflection possibly present in all from all the planes. However, the reflection necessary absent from the none. However, for the body centered H, for the H plus K plus E1, then your reflection will be present, and then your H plus K plus L is odd, then your reflection necessarily absent. And for the phase center H, K, and L unmixed, that is all odd or all even. And for the H, K, and L are mixed, then your reflection will be necessarily absent. And then this is your systematic absences. So permitted reflections. So for the simple cubic 100110111 2002110, and these are if we see, all will be the present. All these all are present. And for the BCC, your sums would be even. So 1 plus 1 is 2, and 2 and this is 4. So these will be present. And for the FCC, your sums would be HK and L unmixed. That is all odd or all even. So here all are odd, all are even, here all are even, all are even, all are odd. So these are will the present. Okay. So there are other factors also. So like the multiplicity factor. So this is depicts that the relative position of your HKL planes contributing to the same reflection enters the intensity. Like for 110, all the planes like 111, 1 1 1 bar 1 1 bar 1 bar and 1 1 bar 1, and for 100 100 010 010 so the value of your multiplicity factor as a function of HKL and your crystal system. Okay, so the relative position of all these planes will contribute to the contribute in the same way as on enters the intensity equation as a quarterly P. Okay. Okay, so let's and also if you talk about the Lorentz factor, so this is based on the angular distribution, that is your difference in the delta theta, delta n by n, and then your geometry factor which affect the intensity. Okay, so So there will be some set of planes which will be oriented exactly to the Bragg's angle diffraction, and then there will be set of planes which are slightly away from your Bragg's angle. So the major thing is this slightly away from your Bragg's angle will still contribute to the intensity. Okay, and then your Lorentz factor is given by 1 by 4 sine square theta cos theta, and then the another factor was the absorption factor. So it is the number by which the calculated intensity is to multiply to allow for absorption. Okay, is a material property. Another thing is the temperature factor. The temperature factor, as your temperature factor increases, the vibration of your atoms will increases, and then your interplanar distance and scale will vary. So this will also a significant effect on your intensity. And this is, so the overall intensity can be written as your structural factor square times polarization factor P times Lorentz factor, which is 1 plus cos square uh, 2 theta divided by sine square theta cos theta times absorption factor, then e to the power minus 2m. So and then the plane which is going to leave the atom, which is going to have the atom which have exactly half the wavelength out of the phase, will be somewhere inside deep of your crystal, right? And then there where the will be destructive interference will take place. Okay, so if meanwhile if anyone has any doubt, please feel free to ask, write in the comment box. And then if we talk about scattering of an electron, scattering by an electron, then we can see that that the electric field which exerts a force on a charged particles, such as the electron, and the oscillating electric field of an X-ray beams. So these will set your electron uh, into the oscillatory motion about its mean position. So the electron which has been set into oscillation by your X-ray beam, it will continuously accelerate and deaccelerate during its motion, and therefore will emit electromagnetic waves. Okay, and then these will have the coherence with your incident beam. Okay, okay, so let's move to the problems. Which of the following statement is correct in the X-ray diffraction? So the intensity of the refracted wave increases in the angle of scattering. Increases wrong. The elastic scattering of X-ray photons by an electron is called Compton scattering. Okay, C is the polarization factor is based because the incident beam is unpolarized. So C is the correct answer. So suppose we have characterized a crystallite material through XRD which has gone through two types of treatment. One is fully annealed and another is heavily cold work. What will be the effect on the X-ray peak broadening? So the cold work material will show higher peak broadening as compared to the annealed material because of the residual stresses. Okay, and then the third question is the supposing an X-ray beam is scattered from a cubic crystal, which of the following set of planes will having the highest intensity in the forward direction? The answer will be 111 because 11 plane will be having the highest multiplicity factor. Okay, because if we see that 111, it will be 111 1 bar 11, then 1 bar 1 1 bar, the 1 bar 1. So therefore this will be the highest multiplicity factor. Which of the following sequence of peaks will appear for a disordered FCC material? Which of the following sequence of peaks will appear for a disordered FCC material? The correct answer will be 111 2 0 0 2 2 0 3 1 1. Okay, because the sum is even or odd. Okay, which of the following condition is true for X-ray diffraction of NaCl according to the structure? The answer is D, that the peak intensity at 0 for HKl having mixed indices, because it will be the subtraction of one Na and then Cl. So then the solution, the structure factor NaCl is 4 times FNA plus FCl, where your HKl are all even. And similarly, so the F is your 4 times FNA minus FCl, and then where the HKl are all odd, and F is 0 where HKl are mixed. Okay, compressive strain in the material will result the XRD peaks. Answer will be V, to shift at higher angles. Okay, then the seventh one is that the structure factor of a crystallite material having atoms sitting at a coordinate 0 0 0 is, answer will be your A, F, because your uh, crystallite material having atoms sitting at 0 0 0, you can use directly the formula and then you will get this. And then given lambda is 1.5 angstrom, FW HM is 2 times 10 to the power minus 7, reading Bragg's angle is 60 degree. What is the average crystallite size of the material? So it can be, the Serre formula can be used at zero point 0.9 times lambda by b cos theta, and theta is in radian, then you will get around 135. So if anyone has any doubts, feel free to discuss. Okay. Okay, then if no, then let's wrap up the class, and then you can mail me also regarding your doubts. Then we'll see you in the next week.